Welcome back to Derivatives and Risk Education. In the previous lesson, we saw how we can use a process called yield curve bootstrapping to derive discount factors from the market prices of government bonds, and then use those discount factors to value bonds consistently with the market. If you missed it, see the link above. You can also download the associated spreadsheet there. Today, we're going to take the next step and dive into the concept of yield to maturity, often abbreviated as YTM. Take a detailed look at how to use the yield formula in Google Sheets and Excel. But before we look at the spreadsheet formula, I will show you a numerical method so you can work out the yield to maturity yourself. This is the exact method that's also used behind the scenes in spreadsheet apps. In the spreadsheet that's attached in the description, you can find all the calculations that follow in the remainder of this video. As always, this is a Google Sheet file that anyone can access. You don't need a Google account, but you can download it as an Excel file if you prefer. Now, what does yield to maturity actually mean? Simply put, the yield to maturity is the total return you will receive if you buy the bond at its current market price and hold it until it matures. Crucial assumption is that all coupon payments are reinvested at the same yield. It's expressed as an annual percentage rate. Unlike the zero coupon discount rates we discussed last time, which was specific to each year, yield to maturity is the single discount rate that, when applied to all the bond's future cash flows, equates their present value to the bond's current market price. We'll see in an example in a minute what this means in practice. Finally, as it is a single number, it's a convenient way for investors to compare different bonds. Now, to keep things consistent, we're going to continue with the same example we used in the previous lesson. Bond with a 3-year maturity, annual coupon of 6%, and a price of 103.43. As a reminder, the bond's cash flows are a coupon payment of 6 in year 1, again 6 in year 2, and 106 coupon plus principal in year 3. So, we want to find the yield to maturity of the bond. As we said, this is the single rate that if we use it to discount all the cash flows, we get the market price of 103.43. So we have the following equation. The price of 103.43 equals the sum of the present values of the three cash flows. If you're unsure about this formula, have another look at the previous lesson 10 where we went through this in detail. So we have this formula. Now, how can we find the yield to maturity? First thing we want to try is to solve for the yield to maturity. Solving for what we want to know is always the preferred approach, as we then have a formula which we can use for quick calculations. Here, unfortunately, we cannot solve for the YTM, as it appears in 3 different places. So what could we do instead? In finance, if we cannot find a closed form solution, we will often use some kind of numerical method. We'll talk more about different numerical methods in future lessons. The specific method, which is used for yield to maturity behind the scenes in spreadsheet formulas, is the Newton-Raphson method. We'll go through the steps for this here. We'll keep the maths to a minimum and focus on the intuition. Newton-Raphson is an iterative approach, which you can think of as a smart version of trial and error. I'll go through the steps now and will explain along the way why we do certain things. First, we choose some yield and calculate the present values of the bond cash flows. Let's say we use for the yield to maturity the same value as the coupon rate, 6%. Let's see what that gives us. For the first step, I will go through the full details as a reminder of how this works. So we discount the cash flows using 6% as shown here. Year 1, 6 divided by 1 plus 0.06 to the power of 1. Year 2, 6 divided by 1.06 to the power of 2. And year 3, 106 divided by 1.06 to the power of 3. Again, all the details are also in the attached spreadsheet. Summing these up gives us a total present value of exactly 100. This should not come as too much of a surprise. If the discount rates are the same as the coupon, then the bond trades at par, a price of 100. But our target price is 103.43. Since our calculated price is lower, means our discount rate of 6% is too high. We need a lower rate to bring the present value up. Let's now try 5% and calculate again the PV. From the spreadsheet we see that the present value this time is 102.72. Again, full details are in the attached spreadsheet. We are much closer to the target price of 103.43, but the price still needs to be a bit higher. So we need to lower the yield a bit more. Don't worry, we won't just keep guessing. We'll be a bit more clever this time. When we lowered the yield by 1%, from 6 to 5%, the price went up from 100 to 102.72, so by 2.72. So, a 1% change in yield gives here a price increase of 2.72%. We saw that at a yield of 5%, the PV is 102.72, so we still need the present value to increase by 0.71. We can therefore guess that we need to lower the yield another 0.71 divided by 2.72 of 1%, which is 0.260%. So we will guess a yield of 5 minus 0.26, so 4.740%. This is essentially the Newton-Raphson method. For the next guess for the yield to maturity, we use the current guess of 5% minus the amount we are still off by on the PV of 0.71 divided by how much the PV changes for 1% change in the YTM, which here is 2.72. We needed to calculate the PV for two different values of the yield so we could see how much the PV changes with the yield to maturity. We then use that information to work out how much we need to change our guess by. We calculate then the PV in the spreadsheet with as the yield our new guess, 4.740%, and we get a value of 103.45. Now we're already very close to our target of 103.43, so this was a very good guess. Let's fine tune it a bit more with one more iteration, using the same reasoning as before, but now we use the prices we got with the yields of 5 and 4.74%. We use the values for 5 and 4.74 as the PVs for these yields are closer to our target than the PV with a yield of 6%. So, between these two cases, we lowered the rate by 0.260% and the price went up by 0.73. So per 1% change, that is 0.73, divided by 0.26 equals 2.79. We need to lower the PV by only 0.02 from 103.45 to 103.43, so we increase the yield by 0.02 divided by 2.79 of 1%, which gives a yield increase of 0.006%. So we try as our next attempt 4.746. In the spreadsheet, then indeed the PV is exactly 103.43, so we worked out the correct yield for our example bond. Please note that I'm using unrounded numbers in the spreadsheet for accuracy. This is especially important when we are close to the target PV. I want to point out that in the process we followed, we worked out changes in the present value for a 1% change in yield to maturity. This value was initially 2.72 and then later 2.79. These numbers are related to an important concept called bond duration. The fact that the numbers changed has to do with a second order effect called bond convexity. We will look at both bond duration and convexity in the next lesson. Now we saw that the iterative approach allowed us to get to the yield to maturity, and it only took a few steps. However, it can still be a bit time consuming. Thankfully, spreadsheet software has built-in functions to calculate this for us. Though it is important to know that behind the scenes, Google Sheets and Excel are also using the same iterative process as the one we used. So, let's see how we can use the yield function in our spreadsheet. As we saw in previous lessons with other functions, we can see what inputs are needed by going into any cell in the spreadsheet and entering equals yield open bracket, as shown here. We see there are a few bits of information to be provided. First, the settlement date. Let's say we are valuing this bond on May 1st, 2025. Next, the maturity date, which is 3 years from the settlement date, so May 1st, 2028. The precise dates don't matter as long as the maturity date is 3 years after the settlement date. The rate is our annual coupon rate of 6%. Watch out here, the 6% needs to be input as a decimal, so 0.06 and not 6. Price is the current market price, which we're using as 103.43. Redemption value is the face value of the bond, which is 100. The frequency of the coupon payments is annual, so we enter 1. Finally, the basis for day count. This is optional and we'll just leave it blank. We'll talk about this more in a later lesson. Then let's see what the yield function gives us. And there we have it. The yield function gives us a yield to maturity of 4.746%. This is exactly the same as our result from the iterative process. As I mentioned, we followed exactly the same steps that Excel does when working out the yield. So, in this lesson we learn about yield to maturity, what it represents and how to calculate it, both through an iterative process and using the yield function in spreadsheets. Also seen how the yield to maturity acts as the discount rate that links the bond's future cash flows to its present value. The fundamental concept in fixed income analysis and a key metric that investors use to evaluate and compare different bonds. Thanks for watching. If you found this lesson helpful, please like and subscribe. And as always, if you have any questions, leave them in the comments below. See you in the next video on bond duration and convexity.